Hello, my name is Camille Quick, and this is my Physics Lab 5 video where I will be exploring Faraday's law and how it applies to a bar magnet falling through a solenoid modeled as a tube of aluminum foil. Later, I will show a computational model that demonstrates Faraday's law as well. The observed average time it took for the magnet to fall through the tube was 1.202 seconds, while the computed average time was 2.215 seconds. The most important concept in this lab is Faraday's law, which relates a time-varying magnetic field to a Curly electric field. It also states that the integration of the scalar product of the electric field and small displacements around a closed path equates the negative change in magnetic flux on that bounded area with respect to time. I also used Lenz's law to determine the direction of the induced current and the Biot-Savart law to help find the force exerted on each current-carrying ring by the falling magnet. Lastly, I used Newton's second and third laws to calculate the force on the magnet from the aluminum tube as well as to model the magnet's motion from its position and velocity values. The experimental procedure for this lab was fairly simple. Using the help of my fellow classmates, I recorded the time it took for a bar magnet to fall through a 28.8 centimeter tube of aluminum foil. I repeated this 5 times to get an average value. It's important to note that I used an aluminum tube instead of a steel pipe because it would create its own magnetic field that would interfere with the magnet falling through the pipe. The first thing I noticed was that the magnet definitely fell slower through the tube than it would have if it were in free fall. The observed average time was 1.202 seconds with a standard deviation of 0.037 seconds. In this model, the magnet is modeled as a dipole and the aluminum tube as a solenoid with n number of loops or rings. These are the initial conditions I started with to simulate the real-world behavior of a falling magnet. As a side note, instead of using the same magnetic dipole moment from Lab 3, I decided to recalculate it because it was abnormally large. Using the old number I predicted would most likely cause the magnet to move slower in the model because it would create a larger upwards force on the magnet. I was right with my prediction because when I used the old value, 5.691, it took 10.881 seconds for the magnet to fall in the model. The initial conditions given were the constants mu naught, resistivity of aluminum in ohm meters, and gravity. The plot is velocity versus time graph of the falling magnet. These are the measurements of the aluminum foil tube needed for the future calculations. The tube is modeled as a series of conductive stacked rings along the y-axis, which is perpendicular to the plane of each ring. Here I created the magnet with a mass of 0.023 kilograms and a dipole moment of 2.565 and its magnetic field by using the dipole function from Lab 3. The magnet's initial position and velocity are 0. This is the function for simulating the magnet falling with delta t being the change in time in seconds. This is the function for the rate of change in magnetic flux through each ring caused by the falling magnet. Using the change in magnetic flux from the previous slide, I found the current induced in each ring by the falling magnet by dividing the flux by the resistance of the aluminum. The resistance was calculated earlier in this slide explaining how the tube was made. This segment R is the resistance and is found by multiplying the resistivity of the aluminum by the quotient of the length or the circumference of the inner circle of the tube and its cross-sectional area. I used the Biot-Savart law to calculate the force exerted on each current-carrying ring or loop by the falling magnet. Using Newton's third law, I concluded that the force exerted on each ring by the magnet is equal in magnitude to the force exerted on the magnet by each ring. Then I found the net force exerted on the magnet by adding the upwards magnetic force and the downwards force due to gravity. To model the motion of the falling magnet, I updated the magnet's velocity and position using kinematic equations derived from the Newton's second law. This last picture by code plots the velocity versus time graph for the magnet as it falls. The graph shows the velocity of the magnet as it falls into, through, and out of the tube over time. As you can see, the magnet has a constant velocity when it is inside the tube. This visual representation shows the currents induced by the magnet as it falls through the tube. The reason why there were 2 colors in the picture is because the magnet induces 2 different currents based on a given position in the tube. Since the magnet falls downwards in the negative y direction at all points below the magnet, the flux is increasing downwards into the page. This means the magnetic field is going into the page, so then using the right-hand rule and Lenz's law, the induced current will be counterclockwise to make a magnetic field going out of the page to oppose the downwards change in flux. Therefore, the blue ring represents a counterclockwise induced current. This reasoning is opposite for all points above the magnet, which would conclude that the red ring represents a clockwise induced current. If the magnet was flipped, then the magnetic field would go out of the page but decrease since the magnet is falling downwards, so at points below the magnet the flux would be decreasing. Using the same logic in the previous question, the induced current below the magnet will be clockwise. My computational time is a whole second higher than my observed time. This error might be attributed to the magnetic dipole moment. The smaller it is, the less time it takes for the magnet to fall through the tube. The shape of the graph shows that, as I said before, the magnet has a constant velocity when it is in the tube, which means the net force exerted on the magnet is zero during that time. If the resistivity of the aluminum was almost non-existent, the magnet would fall slower because there is a stronger current, a stronger magnetic field, and a stronger magnetic force to oppose the gravitational force on the magnet. If there were holes in the tube, it would create a situation opposite to the previous question. There would be a weaker current, a weaker magnetic field, and a weaker magnetic force.